problems. Interceptions can be missile striking and or can be the rendezvous problems. So for these particular examples on your handouts is this. And let me explain a little bit. Say, for example, for these particular examples, we want to launch something and to meet or to intercept the existing objects on his orbit. So here we involve is two different type of the two objects. One is the object which has been on his orbit there already. The second object is the one we're going to launch from a city we choose, okay, and given the time of flight we choose, okay. So in particular, how can we do this one? So for example, here if we say using our Alaska GI radars here, say we will be able to measure the positions, velocity of a satellite, say at this moment. And this problem using the radar to detect the object that we have learned before, and that is in our chapter 2. If you still remember that portions, okay. And then from that way, basically here we know is for this object, say for satellite, we can measure the say R1 is R and V. Okay, so if we can measure the R and V by radar. Okay, and so if you remember for this case, we have this note is we using radar to measure rho and rho dot, right? And that is our radar detections in the PQW in IJK corner systems, whatever. And then from there, we also added up the radius of the Earth. Then we can convert into R and V. If you remember that sections in chapter 2, and that is part of our test before. And I'm going to remind you later. So anyhow, once we have the two things get ready, then we can determine the orbit. How to determine the orbit? If you remember in chapter 2, as long as we have any two of the velocity and vectors, then we can always using the say any program I believe you should have done. And in my personal, I use is ELORB and elements of the ELORB elements of the orbit. Simply using this program in MATLAB, then I will produce the 6 orbital elements, including A, including E. That is the most important things. And even if you like, they also can produce true anomaly new, which means tell you exactly the positions, and also the I, the omega that tell us everything about this orbit. So once we can detect, say at one point here, then we have all the information ready. Got it? Okay. So with those things ready, then what things we can do? So for example, we know at the say according to the numbers here, say at lunchtime at noon, we know the positions here, which means R and V. Then with the orbital informations, we can predict where the satellites would be along the orbit. Say, for example, we can predict the positions and velocity of the orbits at 12:05, 12:10, 12:15, 12:20, by solving Kepler's problems. Right now, we know the R1, V1. This point is here. If we know the given time of flight, 5 minutes, then we can solve for this. If we know the time of flight from here to here, 10 minutes, then we can solve for this repeatedly. Okay? Good? So those ones should be done in your previous homework, right? So assuming you have all the program, I think we have this program developed collaboratively in our classroom. Everyone have that program. So this one should be easy for everyone. Okay. So now the everything predictions of the satellites on his orbit is done. Okay, now we talk about the intersections. Intersection is this. We simply choose a launching site. We simply choose a launching site on the surface of the Earth, say Fort Greely. Fort Greely basically is a military site for launching that's called the missile striking program, right? I believe. One is Fort Greely, and one is in California. The other one is in Hawaii, and that's the United States. That have three. That's I know the three sites. Basically, that is for the missile striking programs. Okay, so now, for example, say this is a satellite, or it doesn't have to be satellite. That can be any ballistic missiles. So that means right now, okay, I will talk about that one after you shut off this one, but not now. And for this one, right now we have the launching site. For example, we want to we want to intersect, not to intersect, we want to meet the satellite, say, for example, here, not here. Say, right now we at 12, at noon we know the satellites. Our goal is, meet the satellite at, say, 12:20. Okay. So that is our goal. So that means in this way we have to know first is where is the location of the satellite at this moment. So given the time of flight from here to here, 20 minutes, so by solving this problem, we know the R2, we know the V2. In particular, we know the R2 precisely. Okay. And now we want to launch it, and how to launch. The launching, that means we have to launch a rocket and then shooting into the sky per certain amount of the flight of time, and hopefully that rocket can bring these things to meet in space here. Okay, so what is that progress? Given this, we know the launching site. The launching site has its own radius. I would say the launching. Okay, we can determine the launching site, which means his locations in IJK. And for this one, we know also this is position. Let me call the R2. Okay, so assuming if given this is R1, R2, then we're solving Gauss problem. R1 is the position of the launching site. R2 is the where we're going to meet the satellite. So we both know these conditions here, right? And now the remaining is as long as we can determine delta t, then by solving the Gauss problem, we would know how fast the launching speed we need to come up with to bring that thing to meet here. Okay, so now the remaining is given what is the time of flight for the rocket to launch from here to here. So they have to prepare the launching procedures. Say, for example, that would take 10 minutes. So once they detect the satellite here, they decide to launch, then they start with the launching procedure taking 10 minutes. So say allowing them only 10 minutes of the time to reach. So basically from here, for example, from here to here, we say the time of flight is 10 minutes. And for the first 10 minutes, that is to prepare the launching procedures. Okay? So right now we have this one. So solving this problem, we know the V1. The V1 is the launching speed, the speed at the launching site. Okay? And that speed, we're looking at here. This is the speed, the absolute, the total speed at the launching, and part of the speed will be provided by the rotation of the Earth. And rotation of the Earth, that is quick. How to do that one? The rotation speed on the Earth's surface. So if this is I, this is J, this is K axis, and this is the equators. Okay, and we can calculate how much the launching, the rotation, the surface speed. So basically, this is the surface speed due to a rotation that can be calculated by the radius of the Earth multiplied with the rotation speed of the Earth. Right. So that one, if we do that calculate, I think in our textbook, but here I think that is about 15 something feet per second. And that is almost 0.4 kilometers per second. And that is very fast. Okay, that is very fast. But anyhow, this is our calculated for needed launching speed. Part of that one can be provided by the surface speed of the Earth's rotations at the launching site there. So that means for launching rocket, we only need is this delta V1. So that means from here we can determine what is the flight path angle at the launching site and to shoot into sky. That is the one provided by the launching procedures there. Okay, so everything we determine, then we can meet the things, the satellites there. Okay? So you know the procedures, right? Okay. So right now we have down here, then this is the V2. So that is this one, this V2 is calculated by our Gaussian, by solving the Gauss problems. Okay. And this is the satellite speed. The satellite at this moment is here, and at the moment is here. Let me call that is the V, and that is the satellite, and satellite at the second point. So that is the speed of the satellite on its orbit at 1220. So this delta V is the one that once we have, say, the intersection to that point, we need to operate delta V change, which means we need to do the orbit maneuver such that we can change and to align to that directions. Be good? Okay, so usually this is a procedure if you say, I think just about 1 or 2 weeks ago, United States, they launching another kind of logistics supply to international office, not international office, international space stations, to provide the on-site astronauts certain quite a few supplies for Thanksgiving. If you watch the news, they have their turkeys. Basically, that is a similar procedures like we presented here. They meet the international space stations on his orbit by choosing appropriate launching time and the time of flight meet there. And once they get there, they do a little bit maneuver or the chasing maneuver a little bit, and to meet with the cargo, meet with the ISS. Okay. So that is the general procedures here. And the issue is this. Here you can see we have to know the launching site and R1, how to calculate R1. That's the first issue. The second issue is how to determine the surface speed and at the launching site and due to the Earth's rotations. This here I show you is on the equator. If we have a launching site, say at, for example, Fairbanks, which has the latitude about 65 degrees, and that speed is much lower than here. Okay, so so how to do the kind of detailed calculations, and can I leave that to you for your exercise or no? This is our textbook, only give kind of the schematic description of the problems. I think that's it.